Thank you so much. Thank you so much, Jeremias, for buying all that time, and thank you so much for your patience. Yeah, I'm actually so happy to finally attend JSHeroes. Like, I'm really in my happy place. Even with the projector problems, this is still my happy place right now. So, yeah, I'm also really happy to be back in Cluj. So I live in Scotland now, but I actually grew up in Cluj. So last time I was here, actually, I was this high. I think maybe high as the H. I was like an H. And yeah, I think, you know, when people ask you what's your earliest memory, I think my earliest memory is actually from when I was like 3 or 4, and I was supposed to go with my mom to the statue in the center of Cluj to see these pigeons, right? Like, I was crazy about these pigeons because they were just so chill around humans for some reason. And while on the way there, my mom decided to stop in a store, and for some reason, while she was distracted, I decided to just wander away. I got lost, of course, because I was 3, I had no sense of direction, and I started crying. Some people saw me, they took me to a police car. I ended up at the police station being declared a lost kid, and my parents found me there 3 hours later, probably the most worried they've ever been in their lives. So everyone was happy. They actually threw me like a party like a few days later. This is me in Cluj, like one of the first pictures I have. And yeah, so not much has changed. Fast forward to the future, I still easily get lost. Nowadays, I easily get lost in big spaghetti code bases where I don't know what I'm going to affect, right? So if I change anything, I don't know who I'm going to break. But this is unavoidable. Like, in today's growing complexity of the JavaScript ecosystem, teams are facing problems of scale like we've never seen before. And that's what we're going to talk about today. So we're going to look at what kinds of problems teams are facing, how monorepos can help, how to keep your monorepos code manageable, and then how to keep it fast. I do work for a company called Narwhal, so I mainly do day-to-day monorepo consulting. So I try and go to different companies, and I look at what kinds of problems they have, why is their CI slow, why are developers not collaborating enough. And Narwhal are also the creators of an open source tool called NX that helps you manage monorepos, and it does build tooling. So for a moment, let's put on some VR glasses, and let's jump into a simulation, right? So let's see like what kinds of problems you can have with multiple repos. So you, in this story, you're like the main developer in charge of building a new pizza store, right? That specializes in pizza and pepperoni. So you use Create React App, you bootstrap the application, you push the code to GitHub, and then you continue working productively for the rest of the week. In the meantime, another team gets tasked with building the admin management side of this app, right? This is for the managers. One of their developers used Material UI before. So they have a short deadline, so they decide to just use that, right? Quickly. They're going to continue working productively, and they push their code to GitHub. This is fine, right? Like, it's 2 separate teams working in 2 separate repos, right? It's a perfect scenario, and teams usually go with this setup because it confirms them autonomy. So they can decide who can contribute to their code, they can choose their own libraries, they can deploy whenever they want. But this kind of isolation can do some harm in the long term, especially when you both have to align to the same goals of the company. So while these 2 teams are building cool stuff, one of the product owners sees that they kind of look a bit different. It would be nice if they had a consistent feeling. So they decide to use a shared design system. For the shared design system, they decide to use Chakra UI as the base layer for the components. And the admin team is not that happy, right? Because they now have to redesign their app to work with the new components. If only they talked with the other team before. But they do all that work, they extract the components into a third repository, and now they have to publish them to some internal registry so that the other 2 apps can consume them. Right? This is important. To share code between multiple repositories, you do have to publish them at some point, like you do with an open source library. But suddenly, you find that in a very narrow layout, this shared button that we just extracted begins overflowing awkwardly on small screens. This is a bug, right? You need to support mobile. So there's a small panic because you have a release next week. But you, as the hero of this story, decide to make a fix to the shared components repo. The fix gets merged in, and whoever has access rights first needs to deploy a new release of the shared components, And then, to use that, you have to make another PR to your own repo to increment to the version number that contains the fix. Right? Same as you would do if like, React releases a patch, you have to upgrade your package JSON file. While this is happening, the admin team might not even be aware that there's even a bug that their users can encounter at any time. This doesn't scale well, right? As more and more projects appear in this repo owned by separate teams and complex dependencies start forming between all the projects, teams might start diverging in terms of what versions of the shared libraries they use. Some teams will decide to upgrade libraries, some will delay upgrading because it's risky. You might have some pizza widgets that you want to load into the different tabs. There are no mechanisms stopping the teams from having different React versions. There's nothing stopping them. So who knows what might happen when you try to load components from React 16 in a repo on React 17, right? There's another problem, which you might have faced even if you work in a single repo on a single app. You might have a backend service that needs to coordinate with the front-end apps. This will have a common interface that they need to share. If the backend team changes this common interface, they might break the front ends in production if they're not careful and they don't coordinate manually afterwards. Everyone will be on different versions of these libs, afraid to make changes or do upgrades, operating in silent silos. This kind of isolation harms collaboration, which is why teams end up preferring to just duplicate code rather than extracting it to a shared place, because it's much easier and less risky. We now take off our VR glasses, and we remind ourselves it was just a simulation. We have a cup of tea, and we sit back at the laptop, and we decide to Google for some solutions. This is when we might come across the term monorepo. A monorepo simply means putting all these projects and apps in the same Git repository. You still have separate teams contributing to separate apps in this repository, still deploying on their own schedule, but all pushing and pulling from the same Git repository. And it doesn't have to be just JavaScript apps, right? If you have some microservices written on Go or C#, you can put them there as well, right? There's nothing stopping you from doing that. It seems weird. But Google, Microsoft, they already have all their code in a single repository. They already do that, like Gmail, Google Search, Google Docs, they're all part of the same repository. Most of us are not operating at that scale, but, but let's see what we can learn from that. If you were to start a monorepo from scratch, let's say you create an app, you push it to GitHub, and then you set up CI for it so it validates your pull requests. When the admin team comes in, they can just add their app in a folder right next to yours. They don't need to set up a new Circle CI account because they can try to reuse the setup that's already there. They don't need to set up Prettier or ESLint because that's already been set up by the pizza team before. And if they want to change that, well, they can collaborate with the pizza team to decide on a common set of coding standards. So we're already moving as an org in that direction, to everyone being kind of on the same standards. And if you want, you don't have to, but you could even extract a package.json file at the root of your workspace. That way, if you have different projects, they would all be pointing to the same node modules folder, to the same package.json file. It seems weird, but they would all be on the same versions of React. So whenever you deploy these, you know they would all work with each other. And when the time comes and the admin team needs to decide what they're going to use for their component library, they can see that another team is using Chakra UI, so that might weigh in on their decision to use it as well. If we want to extract some shared components, well, that's easy. You just right-click, create a new folder, and then import those components into the apps. You don't need to set up a separate deployment pipeline for these components because they're just imported from source. And if we need to make a change to one of the buttons, let's say we change the default theme from light, we change it to dark. Well, the pizza team is already using our button. So we might have broken them with this change. They're expecting that button to have a light theme, but now we changed it to dark. So we could have potentially broken them. This is the kind of hidden breaking change that could have caught the pizza team by surprise in the previous simulation. If the change logs are not too clear, or they somehow miss that change when they upgrade, this kind of bug could sneak into their app. But in this scenario, we can fix it in the same atomic commit and revert their button back to the light theme, and then submit a single PR. Because we're all on the same ESLint rules, the same formatter settings, all the code is in the same place, it's much easier for developers to have a go at changing each other's projects. So we call this developer mobility, and it's one of the reasons why collaboration tends to increase and eventually become the norm in monorepos. The whole code base will start moving faster towards the common goal, and eventually development velocity will increase as a result. So the assurance of these atomic commits cannot be overstated. In a timeline of commits in a monorepo, at each individual point in time, at each commit, you know that everything works with everything else. So imagine having the backend service in there as well in the monorepo. Well, it's easy for someone to just extract like a shared TypeScript interface and import it in both the front end and backend. If the backend team changes that interface, well, the CI might fail for the front end app because they just changed that. So they can appeal to the front end team and communicate with them and try to fix it in the same atomic PR. So at each commit, every project works with every other project, including like any backends you have in the monorepo as well, working with the front ends. This is nice, especially for rollbacks. Like if you want to do a rollback, like for all the services, you can just roll back to a commit and you know that everything's going to work there. So monorepos means having all these distinct projects with clear relationships between them in the same repo. But they're different from a monolith. Right? They're not a single ball of code. There are different teams, and they can continue to deploy these projects as they have done in the past. They can continue to deploy them separately. But now we have a different kind of problem. Who's played Jenga before? Have people played the game? Yeah? It's fun, cool. Yeah, like the point of the game is for you to take pieces out of the tower and you slowly put them on top, and eventually the tower gets more and more unstable, and whoever makes the tower fall loses. So whenever you start the game, the tower is firm, it's stable, it's perfectly balanced, right? It's beautiful. But as the game progresses and people slowly start taking pieces out, that beauty will start to degrade more and more slowly until eventually it falls. And everybody blames the person that made it fall, right? Like it's their fault. Like, oh, if they've just been a bit more careful, they say. But really, this game works because of the effect of how much imperfect human actions can compound over time, leading eventually to that one unlucky soul having to take the blame, right, for everyone else's mistakes before them. So this is what happens with any model which doesn't have automated structural integrity mechanisms in place. Over time, as developers leave your team and new developers join, regardless of how many well-written onboarding docs you have, when a lot of developers contribute, when hundreds of developers contribute to the same massive workspace, your architecture will start to suffer. So to implement structure in a monorepo, we need good tooling. You might have heard of Lerna, NPM, Yarn workspaces. These have done these do a good job of helping you manage multiple projects in the same repository. But to see like the full powers that monorepos can unlock for us, let's look at some examples from these more powerful tools. More specifically, I'll give a lot of examples. Oh, it's starting, I think. Yes. I'll give a lot of examples from NX, but a lot of these examples have a core idea, so it can usually be applied to other tools and other kinds of workspaces as well. So what if you think about this way when organizing your code? Instead of creating all these components, buttons, files in your app directly, you instead start extracting these well-encapsulated libraries outside of the apps folder. And you move your code there. You can think of these as like NPM libs, but local to your workspace. Same as with NPM libs, they'll be very self-contained. Each will have their own unit tests, some will have end-to-end tests. They're going to be like Lego blocks, right? Like ready to compose later. So you might have like some shared utilities for formatting dates. The pizza team might extract all of their features into this separate lib. The admin team might have their own libs as well. For the rest of this talk, we're going to look at what kinds of features this structure can unlock for us. So while the pizza team in their shopping cart might have all these buttons and inputs and maybe TypeScript models, these are all really implementation details, and they all really build up and are being imported by that main shopping cart. That's the thing we want to export from this lib. This is what this lib is offering. Everything else is an implementation detail. So we can define an index.ts file where we can control what we want to expose from that lib. And tools like NX allows us to enforce the structure in a monorepo and makes it easy to manage. But now when the pizza team wants to import something from that cart, they can only import what's been publicly exposed from that lib. The less we expose publicly in each lib, the easier it becomes to maintain. Because we can continue changing the implementation, the internal components, without worrying that we're breaking some downstream consumers. So what if we add something else? So apart from that index.ts file, let's say we add this project JSON file in each one of the libs. And then simply, we just define like some tags in there. We can say, for example, like this library is part of the pizza team, right? It's part of the pizza team scope. That's all we're going to do for now. So now, we're going to add a bit more libs into our workspace. So like our top-level apps will depend on some feature libraries, and those feature libraries will depend on some other things. And we're going to have this dependency graph start to form. And we can add those project JSON files in other libs as well. So we can say that these libs here, they're owned by the pizza team. These libs here, they're owned by the admin team. These ones at the bottom, they are generic shared components that anybody can use, and they're not tied to a specific business use case. Because we have all those files now, we can start building an ESLint rule that allows us to configure how those libs are allowed to depend on one another. So we can say that any lib tagged with scope admin can only import other libs from the admin team or from the shared scope, nothing else. There's already a lint rule like this, but you can define, and there are lots of other open source plugins out there and lint rules that can take advantage of the fact that everything is together and analyzable in a monorepo. So now in the admin team, let's say there's like a new developer, they just joined, they're not sure yet how the workspace works. They try, like when they're working on that feature, they see these utilities from the pizza team and they try to import them. At that point, CI might fail. Right, they're going to get a red line, and when they push their code, CI might fail on that pull request. These kind of guardrails help keep our dependency graph from getting out of control. This one specifically gives teams the assurance that they control who uses what they build. They can always choose to collaborate and extract shared components and put them in the shared scope and make them business logic agnostic. But until then, they don't have to worry they're going to break some other team's code when they make changes to their own internal components. And it's really up to you what other tags you want, right? This is an example of using scopes, but you can add like tags for the types of libraries to say UI libraries can only import other UI libraries to keep them like focused on the view. So to summarize, modularizing your code into distinct blocks and then minimizing the API surface of each one of those blocks via index.ts files, and then setting import rules and boundaries between different modules in your workspace, they're all examples of structure. Having mechanisms in place for implementing structure are essential in a monorepo. Think about TypeScript. You don't really need it for a small JavaScript file for just like a few lines of code. But as your file grows to hundreds and thousands of lines, the value of the structure mechanisms that TypeScript brings is immense. So now that we made our code manageable, how can we make it fast? Well, we usually define our CI YAML files so we define like what steps we want running on each pull request. And as we add new apps, we can start chaining some of these commands to make sure that we don't miss an app and we end up with a broken main branch. But this won't scale. As we add new projects, this is going to get slower and slower and slower. I kept showing you this drawing of our project graph. Tools, the modern tools, like most of the tools I showed you, can already infer this graph on their own based on the TypeScript imports. For example, with NX, you just have to write a command, and it's going to generate immediately this dynamic dependency graph, which you can start exploring and see what libraries depend on one another. This is nice, but why is it helpful for making our CI fast? Well, when you submit a PR, you can kind of tell what files have changed in your branch since origin main. You can use a git command for that. And based on where those files live, you can trace what libraries could be affected. And then based on what imports those libraries all the way up to the root, you can potentially affect any of those other features and apps as well. So for example, if I change the button down there, I could potentially break the end-to-end test of the pizza app because it uses that button. But there's no way I could break the admin app because no root from the admin app reaches that button. So tools like NX allows us to extract this logic away in commands like this, and we can start building our YAML file. So we can say, on each PR, test only the affected libs since origin main. Of any project that is buildable, probably your top-level apps, build only the affected ones. Run end-to-end tests on only the affected ones, and run lint on the affected ones. This is as complex as these get, even for larger projects. So you set these up once, and then you can take your hands off of them. So even if you leave the company, long after you've left the company, right, these will continue to make sure your workspace scales, and they're going to ensure that your CI times will always be proportional to the size of your change, to the size of your pull request. But we can make this faster. If you're watching a football game, and somebody scores a goal, like the goal is so good that there's an instant replay, it would be funny if they miss in the replay, right? I swear I'm going somewhere with this silly analogy. But it's the same in our workspace. So when you build an app, it's going to take a while, but eventually you're going to end up with some JavaScript bundles and some terminal output. And if sometime later I run the same command again against the exact same source code, well, I expect the exact same JavaScript bundles and the exact same terminal output. So what's the point in doing all that work again? This is the magic of a distributed caching mechanism. It's a central service that constantly listens to what commands people are running in your workspace against what source code, and it ensures that no work is ever done twice, ever. So if I run some tests, CI server might go, like the distributed caching server might go like, hey, somebody ran these tests a while ago, and they had the exact same source code as you. Spoiler, the test will pass. You don't need to run it again. Here are the results directly. Another example of this might be your CI is constantly testing and linting and building all the affected libs in each commit. So when I come into work in the morning and I just pull latest and I try to build the app, well, there's a high chance that CI might have already built that app before on the source code that I just pulled from main. So we can just instantly replay the computation that happened on CI on my local machine. I'll get the exact same JavaScript bundles, the exact same terminal output, but the difference being that my command will take 5 milliseconds because it's being pulled from the distributed cache. And this is why it's important to to think about libs when building up your workspace. Besides being your units of architecture, where you control like public and private, and you also control module boundaries, these are also your units of caching. So the more of these well-encapsulated libs you have, the more granular decisions systems like affected or caching can make about your workspace. And the more cache hits you might have. But this is great only for the average use case. On average pull requests, only some libs will be affected. And from those affected libs, a lot of them will be retrievable from cache. But sometimes you might have a lib that everything in your workspace imports. In that case, if you make a change to that lib, you're going to have to retest, relint, run end-to-end tests on everything in your workspace. And nothing will be retrievable from cache. If that takes 2 hours, it's a no-go. Even if it's 2 hours once every couple of weeks, people will avoid making changes to that utilib just because of this. So at that point, we need to start thinking about splitting our CI on separate agents. So we might run build on one agent, test on another, lint on another, end-to-end on another, right? We have to parallelize this at some point if we want to scale. But this is not ideal. Your builds might take way longer than your lint tasks. So you have this one poor agent doing work for a whole hour, while this other agent just sits there doing nothing when it could be helping the other agent in the meantime. And this can get more complicated. You might have some end-to-end tests that depend on the app getting built first so that it can serve as JavaScript bundles. And the app getting built might depend on these 2 other libraries getting built before it. In that case, you need to run all these tasks on the same agent so they can have access to each other's outputs on that agent's file system. So tools like NX or Bazel from Google was actually the first one to implement something like this. They allow you to specify how tasks depend on one another. So you can specify that end-to-end tests depend on the build of their dependencies first. This allows us to enable something like distributed execution, which is when you define all of your steps in your top-level agent, same as you would do, right, if you wanted to run everything on that one agent, but you then created these worker agents at the bottom, and instead of statically specifying on each one that we want build, lint, or lint on another, we instead tell them to listen for tasks from the central orchestration server. So the first one might get some lint tasks and maybe a build. The second one might get some builds and maybe some tests. The third one, it might get some tests and some more lint tasks. The orchestration server at the top knows from historical runs how long on average tasks take to run in your workspace, and it also knows how many agents you have, so it can make sure to distribute everything equally among all the agents such that you have no idle time, and you're finishing this as quickly as possible. When the builds are done, we can add the end-to-end tests and we can split them up. But check this out. On that third agent, it ran some tests, and then it ran some lints. But our end-to-end tests need the bundles of a build. Where would they get that? Well, because we told our build system how tasks depend on one another, it knows that the build that those end-to-end tests need, it already finished on this top-level agent. And because of distributed caching, we can use distributed caching to replay that build computation on the agent that needs it. So we can use distributed caching to also easily move computations between different agents, like make them jump from one agent to the other. So we are suddenly not limited by how tasks depend on one another when deciding how to distribute them. So now we have this dial where if our CI gets slow, we can dial it up and add more agents, and then the orchestration server will make sure that tasks are again equally distributed. Or if it gets too expensive, we can dial it down and reduce the number of agents. So monorepos co-locate information. They bring together all the information about how projects depend on one another and then how tasks depend on one another. So smart build tools can stack optimizations like we just showed, like affected, caching, and distributed execution. They can stack these up on top of one another to make sure your CI and your builds are as fast as possible. This is the hidden side effect of monorepos. But monorepos are not just about fancy tools. They can change an organization. They introduce new ways to think about your code as co-located distinct blocks that have relationships between one another. They add consistency and lower friction when creating new projects and when refactoring code at scale. And they facilitate code sharing and collaboration between the devs. So thanks a lot. I really want to encourage you to check like that website there, monorepo.tools, is a good summary of what we talked about, and it compares all the tools that are currently available in this space and what each one offers and the pros and cons of each. So it was really humbling to do this for me today. I've been admiring your community for a long time and what you've built here. So thanks a lot, and let's speak after this if you have questions or reach out online. I'm happy to chat to every one of you. So thanks a lot.